Welcome everyone to the 34th meeting of New Directions in Group Theory and Triangulated Categories. Today our speaker is Paolo Stellari from Milan, and the title of his talk is Stability Conditions in the Trivial Canonical Bundle Case, Hilbert Schemes of Points. Please go ahead, Paolo.
Yeah, so thank you very much for the invitation. It's really a great pleasure to talk at this lecture series. So yeah, the talk is about, as you mentioned, stability conditional Hilbert scheme of points. So we are mainly deal with hyperkern manifolds. And so the idea is to report on some joint work, partially in progress, with Chunili, Emanuele Macri, and Zhao. I'll try to make clear which parts are complete, essentially the part concerning hyperkähler, and which parts are still a little bit in progress, which are essentially those related to very general abelian varieties in arbitrary dimension. Okay, so the point is that, given that the title of the lecture series, I was assuming that not everybody is familiar with the language of stability conditions or are used to also to the basic results and definitions. So my idea was to have a first part with a gentle introduction to this subject, which might be boring for the experts in the audience, if any. I have no control on the people in the audience at the moment. So yeah, so you can sleep, if you know the material, you can sleep for a while and then wake up if you want. Just to listen to the new results. Okay, so the idea is essentially to, as I said, to use examples to motivate why the result I'm going to talk about is possibly non-trivial and of some interest. Okay, so yeah, so the first part, as I said, is about setting a motivation, right? And I would start with first of all the categorical setting, and so we'll start with X as small projective scheme. Some parts of this discussion are going to work over an arbitrary field, algebraically closed field. Some parts are only working over C. So let's assume, for just to be safe, that we are almost always over C, right? And so, yeah, whenever we are in presence of such a guy, we want to deal with we are interested in a special triangulated category, which probably most of us love and use, which is actually the bounded derived category of coherent sheaves, right? And according to the tastes of the people in the audience, you can think of this as a category of perfect complexes on X under the assumptions we are working in, of course, or in a completely equivalent way as the category of compact object in a bigger category of quasi-coherent sheaves. Okay, so whatever is your favorite language, this is identified with any of these categories. Okay, so and the question, which the way I'm stating this, of course, is a little bit naive. The question one is, so how can we use this triangulated category to do geometry on X? So this is going to be our basic question, right? And of course, the answer essentially depends very much on the taste of the person that is working with this category. Let me sketch at least some possible directions and some possible instruments we can use to do geometry out of this triangulated category. So the first one is by using semi-orthogonal decompositions. So essentially, we look at the way the category is generated by smaller pieces, right? And so that's the standard notation. So we take admissible subcategories, a finite number of them, A1 and N, right? Admissible means that the embedding has left and right adjoint, as we know, right? And the assumptions is that the category is actually generated by these the objects in these pieces. That means that all objects in the derived category can be obtained by extensions, direct sums, direct summands, shifts of objects in these categories, right? And of course, we know that from one category to the other, we have morphisms in this direction, but we don't have morphisms in this other direction. So that's the notion of semi-orthogonal decomposition, which of course opens up completely different research topic, which is about which piece or which pieces in this semi-orthogonal decomposition actually encode the geometry of the variety itself. So instead of looking at a big category, you can look at a smaller one and probably relate the smaller category to the geometry of X and work with this smaller piece. I mean, this is a fast-growing research subject, which I would say it goes under the name of categorical Torelli theorem. So how we can recover the birational geometry or the geometry of X out of some relevant pieces in this semi-orthogonal decomposition. Okay, so there are some spectacular results in this using these techniques. Of course, there are also problems. So in particular, these semi-orthogonal decompositions are by no means canonical. In some cases are interesting or related to the geometry, but they are not canonical. And that's not the path we'll follow during this talk, okay? So another possibility is to endow the triangulated category dbx with higher categorical structures. Of course, here you can, again, choose the different directions, many different directions. So you can look at higher categorical enhancements, okay? And that's one possibility. And of course, this strategy is very much related also to the possibility of describe how the category is generated. So there are non-trivial relations between strategy one and this second strategy, right? Using higher categorical enhancements. Or there is another possibility. So instead of enhancing the category, we put additional structure on the category. And these are what we call stability structures on the triangulated category itself. And this is going to be the content of this talk. Okay. At some point, I will briefly mention when I will be interested in discussing examples, right? How this strategy, which is the main one we want to adopt here, is related to the first one. Okay. At some point, we'll discuss all this very briefly, but I'll try to say something meaningful in this direction. Okay. So this is all about the general stuff about the categorical setting, and now we want to move a little bit closer to the geometric setting. And right, and so yeah, as the title and the abstract suggests, we would like to we will sorry, one has to be white. Okay, we will also in this case almost always assume that the canonical bundle is actually trivial in all the examples we want to discuss, right? And and in this case, under this assumption, right? So we know that by a celebrated result by Boville and Bogomolov, so we know that up to a finite étal morphism. So let me say that X is the product of, and here we get, three different, three very different classes of algebraic varieties. On one side, we have abelian varieties. Right, which from the complex geometric point of view, they are just torides. So yeah, let me write like this. It's very sloppy. Yeah. And then, so I'll use the notation AV for those guys later on. And then there are Calabi-Yau manifolds. So here, essentially what I care about is that the fact that hi of OX is equal to 0 when I runs from 1 to dimension of x minus 1, right? And the example we'll keep in mind also for later user is the case of quintic threefold. Okay, a smooth hypersurface of degree 5 in P4, right? And finally, we have the, this will be, yeah, we use the usual shorthand Calabi-Yau for CY for those. And then we have the irreducible holomorphic. Symplectic manifolds, right? Right, and so here we want them to be simply connected. And plus, right, H0 omega 2 is generated by anywhere vanishing everywhere non-degenerate holomorphic 2,4. Okay, and we'll use the shorthand IHS for those. Okay, so right, so we fall under these three classes of varieties, and essentially the whole point of this talk is to say something meaningful. Essentially, in the third case, right, for irreducible holomorphic symplectic manifolds, and as we will see also for abelian varieties. Okay, we'll mention the results which are known also in the Calabi-Yau manifolds case, right at the end of the second part of this talk. Okay, but as we will see, we'll be very much interested in this class here and this class here. Okay, right. Yeah, before proceeding, of course, I want to warn the non-expert people in the audience that under the assumption that the canonical bundle is trivial, then the triangulated category dx is highly non-trivial. So it means that strategies 1 and 2 are problematic, as we will see, and the answer to the way we can use strategies 1 and 2 to answer question 1. So the idea of use the derived category to produce interesting geometric results is in a sense highly non-trivial as well. Okay, let me mention some pathologies, which are of course very well known, but let me just list some of them for those of you, just to attract your attention on the fact that the results we'll discuss, yeah, they need a little bit of work to be proven. Okay, so the first observation is that the category is indecomposable. So that's a classical result. Due to Bridgeland, Bondal-Orlov, it's essentially not so difficult to be proven, and it means that the first strategy involving semi-orthogonal decompositions cannot be applied directly. So we'll see that anyway. Semi-orthogonal decomposition they play a role in the study of the sort of non-commutative deformations of trivial canonical bundle surfaces, but they cannot apply to study the derived category itself. And so we fail decomposing the category. So we can take a different perspective. So we can try to use a sort of representation theoretical approach. So we look at the group of autoequivalences and we see how it acts on some interesting vector space associated to the variety, namely, for example, the homology of the variety itself. And so here there are plenty of results. You started from Mukai, Orlov, Bridgeland, Bayer-Bridgeland, just to mention a few, right? And but unfortunately, also in this case, already in dimension 2, the description of this autoequivalence group, even though you can give a pretty nice description of the action of the autoequivalence group on these vector spaces, the group itself is very mysterious. So also the autoequivalence group, is in general very complicated to be used. And just to mention a last point, it's not a sensible birational invariant, for example. Okay, so itself, it doesn't recover the variety up to isomorphism or birational isomorphisms. Okay, sense that I mean, we have examples of varieties which are not birational but whose derived category is are equivalent. And in dimension 2, I mean, for surfaces, for K3 surfaces, there's source of very interesting results. And I mean, in a sense, it explains how rich is the relation between the geometry of K3 surfaces and the homological algebra of triangulated category. Okay, so this is a little warning. Okay, so the canonical boundary is trivial. We have a sort of nice classification of the varieties of this type, to finite automorphism. We have our favorite category, but this category is going to be complicated with respect to all possible strategies we listed before. Okay, good. Right. So yeah, given this warning, now we want to start. Describing a strategy to endow, as I mentioned before, the triangulated category with this additional structure given by stability structure. Okay, and right. So sorry. Yeah. And the idea is to start with, the simplest possible motivating example, which is at the same time also misleading, which is given by slope stability for sheaves. And we'll see why it's misleading and inspiring at the same time. Okay, so we start with a polarized smooth projective manifold, right? And of course, slope stability is actually the datum of essentially two ingredients. Okay, oops. So of course, on one side, we have the abelian category X, right? Which of course, in a trivial way happens to be the bounded, the heart of a bounded T structure. This is a very trivial observation, of course. On dbx, sorry. Oops. Right, and then we have a function which detects a class of special objects which are the semi-stable or stable objects. So then we have a stability function. Right, which I will denote like this. So ZH, which is nothing but minus h to the power n minus 1 ch1 plus square root of minus 1 h to the power n ch0. Okay, right, and of course this is a sort of fancy and at first sight useless reorganization of the usual slope function, which is nothing but the real part of ZH divided by the imaginary part of ZH, right? Which is a usual slope function. Right, n is the dimension of course, the dimension of X, right? And of course, now we can take the pair sigma slope, which is made of these two pieces. So abelian category of coherent sheaves and the function ZH. Okay, so yeah, so in other words, we have a category and we have a function that picks special objects, which are the semi-stable or stable objects inside this category. Okay, and also we know that each object, if non-trivial, can be filtered by using the Arden-Araziman filtration. So each object in this category and then each object in the bounded derived category of coherent sheaves can be generated by extensions, subsequent extensions, by objects which are special sheaves. That means semi-stable, and then after refining a little bit more, stable objects. Okay. Right. So yeah, for the non-experts in the audience, as I said, I mean, the idea of regional was, I mean, very much inspired by the work of Douglas, right, about string theory, motivated by the idea of, I mean, essentially studying also the birational geometry of modular spaces. And right, so the idea was to extend a little bit this definition, so made of these two ingredients plus some additional stuff, right, to the general context of the triangulated category dbx, right? And so now the setting has to be specified a little bit better. So again, we start with a polarized small projective variety, and now we fix also a finite rank free Z module, okay? With a surjective map from the usual, this is the usual Grothendieck group, to lambda. I mean, for example, we can have in mind also, I mean, also remember, I mean, the example before. Yeah, one example is the usual numerical Grothendieck group. Or in the example before, for slope stability, we can even take the lattice which is mentioned over here. So it's the truncated, I mean, the lattice generated by the truncated Chern character. So we stop at CH1. Okay, and so just look at these classes. Right, and yeah, then let me list as usual the axioms. Yeah, the idea is that now, to give a stability condition with this fixed lattice lambda, we have to give the art of a bounded structure, generalized in the situation before, and a morphism, which is we call stability function from Z, from lambda to C, okay, satisfying some properties. So the first one is the usual, I mean, condition that means that the image of Z, I mean, has to be contained in the upper half plane plus the negative semiline with the zero removed. Okay, which is, I mean, what I write here. And plus, we need to have Arden-Ziman filtrations. So as before, we start with Z, which is a function, as the stability function we described before. We construct mu Z, essentially in the same way we did before. Okay, but this makes sense whenever the imaginary part of Z is non-trivial, otherwise it's plus infinity. And then we require the existence of filtrations of this form such that the subsequent quotients are semi-stable, right, with respect to this stability function. And the slopes of these pieces are essentially increasing, okay? Sorry, decreasing, going from left to right. And I mean, this was essentially the first axiomatization by Bridgeland. And then soon after, I mean, by suggestion of Kansiewicz and Soibelman, which essentially comes also from the observation that in the examples, the first example studied by Bridgeland, namely K3 surfaces, I mean, this property was implicit. So, I mean, there is this additional condition, which is the support property, which is, I mean, the formal definition is written there. So it's this quadratic form with these two properties, okay? Negative definite when restricted to the kernel of Z, and is greater or equal than zero whenever I evaluated over a mu Z semi-stable object. Okay, of course, we'll ignore, I mean, in the rest of the talk, this additional property, which looks a little bit weird, even though it's clearly fundamental. Because, I mean, if you sum up the three properties, then you can deduce some important results. The first one is that, I mean, the set of stability conditions, if non-empty, actually, so this is something we have to discuss, right, later. Then it's a complex manifold of prescribed dimension, and the dimension is actually the rank of lambda, okay? And then, moreover, we have a well-behaved wall and chamber structure, and variation of stability allows to detect birational models of modular spaces, okay? And then later on, I mean, in a more recent work joined with these people, with Arenbayer, Martilaos, Avinuer, and Emanuele, and Alex Perry, which is not mentioned, I don't know why. Sorry, I think I have to, yeah.
Paolo, can you this support property I think is new to me. Can you say something about it? Is it like a Hodge-Riemann bilinear relations kind of thing?
So as we will see, I mean, in the case, I mean, of course, in general, it's very hard to get a grip on this additional condition, right? Why would I care about this additional property? So the plan was to discuss a little bit in an example. So for surfaces, where essentially for K3 surfaces is essentially Riemann-Roch, okay, is the quadratic form given by Riemann-Roch, or the usual Giesecke-Bogomolov, a variation of the usual Giesecke-Bogomolov inequality, okay, depending on the description you want to give for the stability conditions, right? So if you want to use the original description of stability conditions on K3 surfaces by Tom Bridgeland, so using the omega B notation, or there is another quadratic inequality that takes care of the support property. If you want to use the language of the alpha beta plane, which we also use for abelian trifles. Okay, in other words, it's a little bit difficult to give a sort of meaningful reason why this property is there, apart from the fact that for stability conditions on K3 surfaces, it's always verified in a different form. It's an inequality. Okay, you probably know the version with inequalities. Now, the standard form is by a quadratic form. And if you wait a little bit, I'll try to say something when I move to K3 surfaces. I'm not sure you are satisfied by my reply.
Thanks.
Nick? Okay. Anyway, so yeah, and then as I mentioned, we know in the examples that are studied, for example, K3 surfaces, two additional properties are true, so openness and boundness. And recently, when we redefined this theory, not working over spec of a field, but in families actually. So we actually realized that we need to add these two additional properties, openness and boundness, to the definition to have nice theory of stability conditions, right? But I will also ignore this. We don't need to work about this to understand this part, which is mostly related to properties of moduli spaces of stable objects, which are not treated in this talk. Okay. Right. Additional questions so far? Okay, so if there are no questions, I would plan to move to examples of increasing dimension and try to use them to convince you that, each time the dimension increases, you have to invent a trick. And then when you get to hyperkähler manifolds, the dimension is very high, so at least 4. And so you are in trouble. So you need something highly non-trivial to define stability conditions there. Okay? So I'll start in a very basic way again. So essentially the point is that, so the question we should keep in mind, which was the one we also discussed before, so I think it's question 3 by now, is let X be a smooth projective variety, say over C, right? And then the question is this stub. Now, to be precise, I should make precise also the fact that I choose a lattice lambda, right, since the very beginning, and then I look at stub X, which is the space of stability conditions. On dBx with respect to the lattice. Lambda is the X guy non-empty. That's the point. So, and once we know this, we know that it's a manifold, we know the dimension, we know a lot of things, we know the local structure, Walling chamber structure, so we can do wall crossing and so on and so forth. But this question is as I mentioned, basic, simple to state, but very difficult to answer already in examples. Okay, and that's the guiding question that we will be present in our talk. Okay. Again, so we start with the basic, probably most trivial example. So we start, again, we are in the trivial canonical bundle case. We work over elliptic curves. I mean, we'll use this example implicitly later on. So let me briefly recall what happens. So in the case of elliptic curves, so I mean, this is actually more general. So it works, for any curve of, for any curve defined over C, so we can, one can prove actually not, it's quite easy. I mean, that this simple example that we described before, so slope stability, where the abelian category is the category of coherent sheaves and the stability function is ZH. So this slope function, rewritten in a fancy way, is actually a stability condition on dbx. Okay, and this is, it's easy also to understand that this is completely false in dimension strictly greater than 1. Okay, so this is not, and that's the reason why I mentioned the slope stability example as a sort of inspiring, but at the same time misleading. So because it works only in dimension 1. Okay, and of course we know more. So in this case we have a complete classification of stability conditions, which is actually also something which is in general rare. So even though you know that the stability manifold is a complex manifold, it's usually quite difficult to understand its topology already. And so the point is that sigma slope is essentially the only non-trivial example of stability condition. On dbx, in the sense that we know that, stub x, here I'm using as lattice, the lattice that I mentioned before, okay, the lambda h, which I described before, is nothing but the orbit and the g+2 twiddle are of this sigma slope. So there is a natural group, which is the universal cover of GL+2, okay, acting on the stability manifold, and all the stability conditions on X are obtained in this way. Okay, so you start with this nice point, and and then the rest is obtained by this group action. Okay, so here, it's easy. You can do as an exercise. There is essentially no support property. So you take any quadratic form on H0 direct sum H2, which is positive definite, and then it would work. Okay, so it's not there's nothing deep here. But if we move a little bit further, so if we move to higher dimensions, so we know that this example is no longer working. So so we move to the case of abelian or K3 surfaces, right? And so here, I will be mainly interested in this case, the Kummer surfaces, okay? So which are minimal desingularization of the quotient of an abelian variety A by -1, okay? We'll use this later on. But in this case, actually, we have to invent something in order to prove that the stability manifold A is non-trivial. We don't need to do it. It was done before, as we will see. But the idea is that we have to produce a way to construct new T structures. This is in general problematic. It's troublesome. And also you need to invent a stability function. And of course, you have to deal with the relation between these two guys. Okay, so you need this compatibility, in particular axiom 1. So the image has to be contained in the upper half plane. That's a mess, usually. Okay. So here are the flames of hell, okay, right? So this is the problematic way to show that the two constructions match together, and right. But fortunately, smart people work on this case before us, so we know how to deal with the stability conditions on K3 or abelian surfaces, right? So So the idea, I mean, slope stability is not working, but we have an intuition on how to proceed. Okay, so we have this pair given by slope stability. This is no longer a stability condition on dx when x is a surface, but we can do the following thing. So we can use this this pair, which was a stability condition in one dimension less, okay, to tilt the category of coherent sheaves in order to obtain a new abelian category, which is the art of the bounded structure. Okay, so in this case, you can work out the example given by, as I mentioned before, the usual numerical logarithmic group, which is H0, direct sum Roseveri group, and direct sum H4, right? And right, so you need to construct a T structure, and so you proceed as I mentioned. Okay, so you have a slope stability. Okay, so with mu h, which is the slope stability constructed out of the stability function z h, and you use it to construct this torsion pair, right? So in other words, you cut the abelian category, which was the art in one dimension less, right? You produce T and F, and then you construct this with a standard procedure A with it as a tilt. Okay, take F shifted by 1 and T, so you get an abelian category whose objects have two homologies in degree 0 and degree -1, and this turns out to be the art of a bounded T structure. Okay, and then you have essentially also a very sort of intuitive way to construct a slope function. So the suggestion comes from mirror symmetry, but also there is one little observation which is tricky but useful. So the point is that what was the real part of the stability function in one dimension less now becomes the imaginary part. And this is going to work also in higher dimension, at least conjecturally. Okay? So the stability function in one dimension less not only gives you the function to tilt the category, but also gives you a suggestion of what should be the imaginary part. Okay? And right, and now here, I mean, the quadratic form, which is going to provide also the support property, is actually the classical Bogomolov-Giesecke inequality. Okay, so the support property is a little bit, yeah, maybe I should write it here and show that it's actually a quadratic form in the sense that, I mean, the function is ch1 squared minus 2 ch0 ch2 greater or equal than 0. Okay, which looks very much like the Mukai pairing. All right, and well, this has to be true whenever you take a semi-stable object with such that the rank is positive. Okay, and if you work it out, so you see that, I mean, using this quadratic inequality, I mean, you can prove that the pair A and Z, where A was the tilt and Z is the function over there, satisfies axiom 1. Okay, axiom 2, which is the one which says that the image is contained in the upper half plane plus the negative semiline. Okay, it's a nice, simple exercise which you can try to do, just using the definition essentially of tilt and of stability function. And right, and this is essentially the basic example we have to keep in mind. So because it illustrates the strategy, right? So you start from one dimension less, it's not working in this dimension, but anyway, we recycle completely the information which comes from one dimension less, okay, to produce something working in dimension 2. And the trick is tilt and move a real part to imaginary part and add a guess for the new real part of the stability function. Okay. Of course, also in this case, maybe might be useful to say that, I mean, in dimension 2, I mean, we have also something more to say. So in particular, if X is abelian.
Can you explain how the Bogomolov-Giesecke inequality is related to the real part? Because you have H instead of C1.
Pardon me? Yeah.
So why is the I mean, should be that why it lands in the upper half plane. I'm not
yes,
sure.
Yes, indeed. Yeah. You need a little calculation. You have to work out, I mean, which is the part which matters in this computation, and in particular, you have to deal with. Oops, sorry. with the F part, which is the problematic part. So the case where, I mean, you have H dot CH1 equal to 0, okay? And you want to show that it lies in the negative semiline, okay? Whenever the imaginary part is 0. And here, I mean, it's a little computation. Of course, it's not straightforward, but I mean, it follows directly from the fact that, yeah, you.
That's okay. I thought that you explained
Yeah,
it.
I mean, I can work it out if you want, but anyway.
Never mind.
HC, the point is that H dot CH1 is 0. I mean, that's the critical point. And then you have to work only with the shift of an object in F, in the additives category F. So those in the additive category F, as you see, are those such that all the Arden-Arziman factors have slope smaller or equal than 0. And then you work it out a little bit. And you see that, I mean, it automatically has a new, the real part of the new Z is automatically negative. So you have to do a little calculation, but the imaginary part is 0. And that's the critical case. Okay. So imaginary part 0, and you have to pick an object in here. And show that for this object, the imaginary part is positive, and so that the shift has a negative real imaginary part. Okay. Anyway, so right. So the point is that also for abelian surface case, more is true. So we know that stub X is actually, to be precise, there is only one. The point is that there is only one connected component of maximal dimension, which is the rank of the Grothendieck numerical Grothendieck group in this case. And so let me write in a very compact way. So it's connected. So meaning that, actually, to be precise, that there is only one connected component of maximal dimension and simply connected. So in this case, at least you can understand the topology. So this is an old work of Daniel, Emanuele, and myself. So long ago, right? For K3 surfaces, I mean, you would expect something similar. So, but here there is actually a conjecture by Bridgeland that says that, again, that there exists a connected component that contains the above the existence is known. So we have an explicit description of connected component contained in the above example, and which is simply connected again. I mean, this is widely open and was proven by Bayer and Bridgeland. When the Picard rank of X is equal to 1. Okay. Yeah. So anyway, for these surfaces with trivial canonical bundle, you know a lot actually. Okay. Now.
Paolo, is the result for abelian surfaces is that old or is it new?
I don't know. It's old. I mean. So, I mean, we had a longer series of paper to prove this conjecture by Balázs. So the fact that, I mean, the image of the, I mean, this is a representation map that maps the autoequivalence group onto the orthogonal group of orientation preserving geometry of the Mukai lattice is surjective, right? And one key ingredient was to study the case of very general K3 surfaces, non-projective ones. So essentially those that contain only one up to shift spherical object, which is OX. So in that paper, which then goes back at least to 10 years ago, I would say, something like that.
Yeah, I think I know that.
Anyway, so you discover that, I mean, if you have only one spherical object, you can describe completely the stability manifold. And that was the example that we were interested in for K3 surface, no projective K3 surface with trivial Picard group, so Picard group which is 0, okay? But then the same technique applies. So you show that also for abelian surfaces which do not contain spherical objects, they don't contain spherical objects at all. I mean, the same techniques applies, and so you can prove that it's simply connected. Okay. Anyway, so it's a side observation of this work about non-projective generic K3 surface, K3 surfaces of a long ago. Okay. Right. So maybe I can spend a couple of words. Okay, time is short, but anyway, I'll try to say a couple of things. So the main application is the usual theory of Macri, which allows you to describe a rational model of classical moduli spaces of stable sheaves on K3 by wall crossing, essentially. But I want also to mention a little result, which connects this theory, which is more recent and known maybe to some of you, but not to all of you, I hope, or I guess, which is this the possibility to construct stability conditions also non-commutative deformations of K3 surfaces. And so, yeah, so these results. So, and with these results, I mean the existence of stability conditions plus this idea that you can study the birational geometry of moduli spaces by wall crossing. Actually, these results have been so recently, so to speak, recently extended to non-commutative K3 surfaces. And this is a work with Arenbayer, Martina Hoth, Emanuele, myself. So, and the point is that, you used to take X in P5 as smooth cubic fourfold. Which is a smooth hypersurface in P5 of degree 3, and then you look at the bounded derived category of coherent sheaves. In this case, you have a similar orthogonal decomposition. So you have 3 exceptional objects and a residual category, which will denote by QX. So the Kuznetsov, what we call the Kuznetsov component of dBx. And this guy here is a so-called non-commutative K3 surface for several reasons. So the self-functor of QX is the shift by 2. Then Nick and Richard Thomas studied the natural homology associated to this category here. And it turns out that is the same lattice and Hodge structure as the homology of a K3 surface. And moreover, these are cubic fourfolds. They fit in families, in 20-dimensional families, and along some divisors in the modular space. This Kuznetsov component is actually the derived category of a K3 surface, an actual one or a twisted one. And so this category itself, which moves in family, can be seen as a deformation along, together with the deformation of X, of the usual derived category of a K3 surface. But it turns out that for a very general cubic fourfold, this category can never be the derived category of a smooth projective variety. So it's really something non-commutative. Okay. So the point is that we can prove. So we prove that stub of this Kuznetsov component of X is also non-empty. Okay, so this works also in non-commutative deformations of this variety. Okay, and so essentially this is all I want to say in dimension 2, and now you want to move to a dimension 3. Okay, and I guess we want to move it to dimension 3, and so in dimension 3 we can work with the case of abelian threefolds, and the example that I mentioned before, quintic threefolds. So abelian varieties and Calabi-Yau manifolds. Okay. Of course, again, we have this problem understanding if stub, so X is of this form, so we want to study stub X and understand if this is non-empty. I mean, at least we know we have a strategy. And we can guess what we should do, right? So we take the stability condition that we define in the case of surfaces, okay? So we proceed as before, sort of by induction, okay? So we take stability condition for surfaces and we use, this, which is no longer a stability condition on threefolds, in order to tilt the category and get a new out of a bounded structure. What was before the real part becomes the imaginary part of Z, and then we have a way to guess which should be the new real part of Z. So the strategy is that use stability on surfaces to tilt and get a new T-structure plus a stability function. Okay, so it's easy to say, but difficult to implement, of course. I mean, and the reason is that, of course, Eyal was asking before, how do you use Bogomolov inequality to prove that this guy lies, the image of the Z function lies in the upper half plane plus the negative semiline. So you, in that case, you have to work a little bit, but it's not difficult. In this case, the point is that you need a new inequality, okay? You need a new inequality that involves higher Chern classes, okay? And that's the key point. So you need to guess which is the Bogomolov inequality that works in order to prove that, this new pair you construct, so the tilt of the previous abelian category and the new stability function, they mesh together, and are such that the image of a non-trivial object in the new heart is contained in the upper half plane. So that's difficult. So the moral is that easy to say, easy to state, but difficult to implement. So difficult that it's also false in general, actually. So in the trivial canonical bundle, there is hope that this strategy would work in higher dimension, but if the canonical bundle is non-trivial, we have counterexamples. So this strategy, in the very vague form that I suggested, fails, okay? There is a new proposal in the ICM talk by Bayer and Macri. There is a new conjecture in there for the existence of stability conditions in higher dimension, which of course avoids all non-counterexamples, but yeah, you have to guess how to proceed. But anyway, so at least in a couple of cases, the ones that I mentioned, so this is going to be a theorem. So this is Bayer. It's also a theorem going back to 5 years ago. So if X is an abelian threefold, then stub is non-empty. Of course, here I should be careful and say precisely which is the lattice which is involved. So I should put a decoration down here, and then I should tell you which is the lambda, but I'm not going to do this, of course. And for quintic threefolds, this is even a more difficult result due to Chunili, which says that the same is true when X is a quintic threefold. Some even more difficult result. Okay, good. But essentially, the story, for the trivial canonical bundle ends here up to now. So now, this was a sort of a historical introduction to the subject, and you see that whenever the dimension grows, the difficulty grows. Okay, because you have a procedure, but you need to have a new inequality in order to show that the pair you construct satisfy all the axioms. Okay, And now, of course, the question is that how do you go on in higher dimension? The question is particularly relevant, right? Because if you start with an IHS, if it's not a K3 surface, then it's something of dimension greater or equal than 4. Okay, so how do you do now? Okay, how do you prove that you can produce stability conditions? For example, in this classical and beautiful example given by the Hilbert scheme of endpoints on a K3 surface. Sorry, so X is a self-referential. So I guess one of these should be Y, I guess. Okay, sorry. Y also here. Right, and okay, so let me state the main theorem. This is proven actually, so it's due to Chuni, Emanuele, myself, and Zhao. And says the following: so for any integer n greater than 1, there are infinitely many IHSS of dimension 2n of type Hilb n of a K3, right? Such that say X, such that stub X is different from the empty set. Okay. Right, so this is a fancy way to so that's the result. It's actually a fancy way to fancy. I don't know if you like it actually, but it's a very sort of quick way to state a more precise result, which I want to write it now here. So this follows. Following precise result. And you'll see why I insisted a little bit, maybe too much, on the lower dimension examples. So on the Kummer surface and on elliptic curves, because the theorem works as follows. So again, by the four of us. So let's mention the first part. So let E1, E2 be elliptic curves. And let, so now we take X to be Hilb n of the Kummer surface associated to the abelian surface given by the product of these two elliptic curves. So n greater than 1. Then, so here we can write, so okay, maybe let me write it in a compact way. So we can also take, say, Y. So I won't care too much about the second part, might be useful later on. So I can also take the Hilbert scheme of the abelian surface given by the product, okay? And then in both cases, we get stability conditions. Actually, we get a family of stability conditions. I wanted to mention. So this closes, it answers the problem of constructing stability conditions for hyperkähler manifolds. So we have infinitely many examples in all possible dimensions of hyperkähler endowed with a stability condition. And then there is a second part which is more about very general abelian varieties. So part 2 and part 3. So if A is a very general abelian variety, of dimension. Okay, let me write first the case of abelian surfaces, because it's more related to item 1. Abelian surface. Then stub of the Kummer surface of A is different from the empty set. Okay, and also part 3 is what I wanted to say before. So if A is a very general abelian variety of dimension n, then stub A is different from the empty set. Okay, I should put an asterisk here and an asterisk here. So I mean, should be warned that this is again work in progress. I think I went over time. So I was planning to say a few words about the proof, but I'm not sure. I mean, I have time to mention something. Any feedback? Shall I say a few words, or you want me to stop now?
It's up to you, Paolo. Completely up to you.
It's up to the audience. Of course, you can leave. So you're free to leave.
Maybe. So
yeah.
when, so in case 2, it's a K3 surface. So for which K3 surface?
Sorry. No, your question is, what are you talking about? We know this result. Sorry. I guess, yeah.
Oh.
Sorry. That's a statement.
Thank you.
Okay. Not only for the Hilbert scheme of the very special, even though they are dense, I guess, Kummer surface is given by product of elliptic curves, but also for the very general abelian surface should be true. Okay. Okay, maybe I can just sketch very quickly the idea behind the proof of item 1. I mean, can I take just 5 minutes? So if you want, you can leave, of course. Okay, the idea of the proof is essentially the following, right? So we want to prove that this guy is non-empty. Okay. And now you work in the following way. So you first prove a theorem which looks useless, but it's actually quite strong. So essentially it tells you that if you take a product of n curves, smooth projective always, okay, so here we have the assumption that the genus has to be greater or equal than 1. But essentially because otherwise item 1 is false, and then we cannot prove also item 2. But anyway, so what I want to say is that if you take P1, it's not true that all stability conditions are geometric. And so in particular, this cannot be true for the product, just to mention. Okay, so it's a technical assumption which might be removed, but not with the proof we have now. Okay, so the point is that all stability conditions on this product, okay, we know that there are, due to the work of Yu Cheng Liu, okay, it's a previous work. So all of them are geometric. And that's a fancy way to say that skyscraper sheaves, they are all stable, right, of fixed phase, okay? So you pick a stability condition, all skyscrapers on this product are stable and with a given phase, okay? And the point there is that the key point is B, okay? So the point is that the stability condition is now uniquely determined by its stability function and the phase of skyscraper sheaves. Okay, this is requires a little bit of work. It's not trivial at all. But I mean, this means that essentially you have an embedding, so the forgetful functor that takes a pair, right, and sends it to the stability function, right, gives you an injection. Okay, an injection from stub to this product. Okay, so in other words, I find it very fascinating in a sense, because it tells you that in this case you can treat stability manifolds as sort of a linear object. Okay, so in principle you could even describe stub X. Okay, so it embeds inside this very nice vector space. Okay. And right, so we know that actually the key point is that we know already that this guy here is non-empty. Okay, but we know a little bit more. So if you work it out, you can be explicit about the stability function. That's the key point, because remember, you want to prove that it's determined by the stability function up to the choice of the phase of skyscrapers. So how do you work? So you take an ample polarization on any of the curves. So you take the tensor product. So you take an ample on the product X. And the point is that you work a little bit and you show actually that you can construct out of these examples given by Yu Cheng Liu. You can give examples such as stability function actually it can be described in this very compact way. Okay, so this is a very fancy way to say that, I mean, what is this? So this is a sign. So, okay, in principle, there is a minus in front, okay, but we don't care at the moment. So the point is that we want to understand what is this guy. So this is a twisted chain character, okay? Okay, so it simply means that you take the exponential of this line bundle, beta plus square root of -1 alpha h times ch, the usual chain character, and you take the degree n part, okay? And where alpha and beta are allowed to vary in these sets, which are mentioned here. Okay, so you see that you get a two-dimensional family of these guys. Now, this is true in general for any product of curves. Whenever you know that the genus is greater or equal than 1. Now let's specialize to the case where you take just one curve and you take n copies of it. Okay, so in this case, the point is that. I mean, given the explicit description of the z function, it turns out that, I mean, it's not difficult to see that, I mean, the z it's invariant under the permutation group, the action of the permutation group on the copies of C, and it's whenever, I mean, if you know that the genus of C is 1, also by the action of the multiplication by -1. Okay. And now, once you know this, you are essentially in business. Okay, once you've proved this non-trivial result that I mentioned before, now you're in business, because instead of taking products of n copies of C, okay, you take two elliptic curves, E1 and E2, and you take the product of n copies of the surface, the abelian surface given by S times S times S. Okay, and you let and now you can have the action of -1. And at the same time, the permutation group on this guy. Okay, and now you readapt a little bit more the argument as before, and you see that Z is invariant under these two groups. And if you analyze these maps, that gives you the embedding of the stability manifold inside this linear space. You see that it's also equivariant under the action of this group. Okay, so in other words, you can conclude that the stability subset, which consists of all stability conditions, okay, which are invariant under this group G, generated by these two groups, is non-empty. Okay, and now you know that on one side, the derived category of the Hilbert schemes of the Humer of S is actually the equivariant category of X. This is Bridge-King grid. Okay, some computations. And on the other side, you can apply, again, an old result of Emanuele, Suchendo, and myself that tells you that you have a natural embedding of this subset of equivariant stability conditions under the group G into the stability manifold of the equivariant derived category, which is nothing but the derived category of the scheme. Okay? So the non-trivial example we constructed here gives you a non-trivial example here. Okay, and then you are done. We're essentially done in a very sketchy way with item 1. Item 2 and 3, I mean, they are conjectural, but we have a clear strategy in mind. So the point is that these have to be proven by deformation. So again, you have to deform the stability function and the heart of the structure. The stability function deforms once you choose I mean, the Z function appropriately, because I mean, this determines completely the stability condition, so it can be deformed. And then you have to deform the T structure. This is something we are working on right now. So the point is that we have an infinitesimal, a theory for infinitesimal deformations of triangulated categories together with T structures, which is due to its work in progress by Genovese, Lowen, and Vandenberg. And now you need to integrate. That's the key point. Okay. Once you have this, we have a trick to induce a stability condition on the very general point, and so you're done. Okay. So sorry, I was a little bit sketching this last part. Thank you very much for your attention.
Thank you, Paolo, for the wonderful talk. I can't wait to read the paper. Do you have any questions for the speaker now? Nick, were you about to ask something?
Oh yeah, no, it's sort of odd, right? Normally, the ones of small Picard rank are easier than the ones of high Picard rank, but you've gone for the biggest ones first.
Indeed, actually, but the reason is, you need to know. The point is that, so you need to know that you have stability conditions on the product. That's the issue. So you have to start with something big already. Here is the product of curves, or product of K3 surfaces, which are product of elliptic curves. And for this also, again, we have this inductive procedure by Yu Cheng Liu, which we can refine, as I mentioned before, but we know that there are stability conditions, okay? And that's, again, a tilting procedure, okay? So we have Abramovich-Polishuk way to construct a stability condition on the product, okay? And we have a guess on how to construct a stability function, right? And we use this to tilt in order to, to extend the stability condition we have on one piece on the product of n-1 copies of C to n copies of C, okay? So we have this inductive procedure to construct stability conditions on bigger and bigger and bigger products of curves, right? That's the starting point. So I agree with you that a priori, it should work the other way around. But no, in this case, so yeah, we start with something with large Picard group. And also, quite surprisingly, if we manage to prove also part 2 and 3, actually, this was a question by Rahul Pandaripande some years ago when we were giving talks about our abelian threefold scales. So his question was, assume we can prove that you have stability conditions on a very special abelian threefold, right? Can you deform the stability condition, right? Can you deform to a very general point, okay? And so, yeah, the idea is exactly the same. So you start with a stability condition on a product of 3 elliptic curves, say, or 4 elliptic curves, right? It's a special fiber, right? And you want to be able to deform to a very general fiber. Okay, there is no, our claim is that there is no obstruction on the level of Z function if you pick the stability condition on the product carefully, right? And then you have to worry about the T structure. Okay, infinitesimal it works, then you have to integrate it, and then you are done. Yeah.
So that is part of what you're doing, the deforming the stability condition with to a general deformation of the Hilbert scheme.
So the point is that, yeah, we would like to complete, the point is that we want to complete where is it? Part 2 and 3 in this problem. Forget about the Hilbert scheme for a second. Okay. Of course, it would be very interesting also, another question. So to show that if you take a very general K3 surface, then the Hilbert scheme of endpoints on it, it does carry stability conditions. Okay. So
what is it that you're deforming? I don't understand what type of deformations you allow.
In the proof of item 2 and 3 we have in mind, we deform the abelian surface or the abelian threefold or abelian fourfold or whatever. So we don't deform the Hilbert scheme. We start deforming the abelian surface, okay? And then we take the Hilbert scheme on the deformed abelian surface. Of course, you can look at something even more interesting. So you could, you can deform the Hilbert schemes all together, okay? Starting from the example we have in mind. This we are not able to do. This we cannot do. So the idea is that you deform the surface, you construct the Kummer surface, and then you construct the Hilbert scheme, and there you have stability conditions.
Do you get from this existence of stability conditions some new inequality on Chern classes that was not known before?
Yeah. Yes, but the key point is that are they useful? This I don't know. Yes, of course you get new inequalities. So can they be used to prove new results? This I don't know. I mean, of course, there is the whole business starting at this point. Yeah, to understand. I mean, this can produce interesting and new results about modular spaces, of course. And if the inequalities we get are interesting from the point of view of stability, we don't know.
Also go ahead.
No, I mean, these are a little bit also implicit. I mean, the point is that this inductive procedure to construct inequalities that they work whenever you add a curve are slightly implicit. So to work them out and see if they can be applied, I mean, I would say it's a second order problem, which we haven't touched at the moment, but it's certainly very interesting.
Is the lattice that you're using interesting?
Here in this case is no. I mean, well, yes and no. It's here in this case it's the, as you said, as you see from the where is it? It's the usual numerical Grothendieck group. So it's interesting in the sense that it's the biggest possible, but it doesn't take interesting slices in the stability manifold. So it's interesting in the sense that you get a big picture, but yeah.
So can I ask a naive question?
Yeah.
Yeah, please go ahead.
So if I understand correctly, you use Markman Bridge-King grid equivalence to sort of turn a derived category of the Hilbert scheme of points into the equivariant derived category of the sort of K3 surface, or the surface basically. And then you use that side to show that the stability condition exists. Is that correct?
Well, yeah. I mean, you first use the, I mean, is the picture that is down here. So essentially, you first prove that this guy is non-empty. That's the key point. Yeah.
Yeah. So and what I was wondering is, I mean, a natural generalization of sort of Bridge-King grid that's been used many times in the literature of this story of Hilbert scheme of points on surface is to consider any x, but instead of Hilbert scheme of points, consider you basically compare the symmetric quotient stock instead of considering the sort of the equivariant category there. So I was wondering if it might be possible to use this to show that if X is possibly a higher dimensional variety which admits a stability condition, then you could say something about the stability conditions on its various symmetric quotient stocks, which would replace Hilbert schemes of points.
Yeah, I mean, why not? Yeah, sure. I mean, so the strategy is quite general. I mean, you cannot hope to be too general, as I mentioned. For example, you cannot hope to use this strategy to prove that Pn has stability conditions by taking P1, 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 P1. Okay, this doesn't work. Okay, so you need, I mean, at least in the version that we have, I mean, you need to have constraints on the curves. Okay, now, of course, the content of this part of the story is completely general. Okay, so the point is that you want to show that this guy here is non-empty.
Mm-hmm.
So okay, you can hope to generalize a little bit the story I told you, but yeah, with some care. I'm not sure it's too completely general. I mean, for example, I can give you an example. So for example, why not looking at the generalized Kummer, right? You can also realize them as quotients. Okay.
Mm-hmm.
Okay. Yeah, but in that case, for example, it doesn't work. So the group does not I mean, it's not equivalent. I mean, we are unable to show that this guy here is non-empty. Sorry, sorry. We are unable to prove that this guy here is non-empty. Essentially, because we have a complete description of the stability manifold. As I said, it embeds inside this vector space. But the stability functions, at least the naive one we can construct, they are not invariant under the group. It must have this group.
I see. So there should be some condition on a group, very non-trivial condition of the group, which tells you that if stub X is non-empty, then stub GX is non-empty.
Yeah, indeed, actually. So that's my point. So. You're probably right. We can generalize the story a little bit more, but not too much, because we know already that what I told you is not working.
It only works for very special groups. Cool. Thank you very much.
Yeah,
I understand this a bit better. Thank you.
Yeah, may I ask something? What do you know about stable objects for one particularly nice stability condition that you know?
So of course, I don't know. Actually,
I mean, something is you know for free. What are easy? I mean, there are easy example, probably skyscraper sheaves. I don't know what.
The skyscrapers, of course, are stable, as I mentioned, because they are always stable of prescribed phase. Now, of course, why not looking at hyperholomorphic vector bundles on this hyperkähler? I don't know actually. So of course it would be very interesting.
I mean, is there thing you know that is not stable? Is there do you know some additional condition on a vector bundle for it to be stable? That is, I mean, can you rule out something? What information do you have?
So I have to be sincere with you. At the moment, very little. So I know skyscraper sheaves, but I don't know much more about vector bundles. Of course, it's a very interesting question, Eyal. I completely agree with you. So we are, I mean, we are at the beginning of this story. We are at the beginning of this story, and there's certainly, I mean, yeah, as I mentioned, I mean, there are a bunch of very interesting stable vector bundles which are around in the theory of hyperkähler manifolds, as you know better than me. And yeah, of course, it would be very interesting to understand if they fit in this picture. We don't know at the moment. Yeah, it's a very interesting question, but we are really at the beginning of the story. So, I mean, so in other words, before studying modular spaces, we want to be sure that we are working with something which is non-trivial, the stability manifold, and then of course the next step would be to study this kind of objects. But yeah, we are, yeah, you have to give us a little bit of time more.
Thank you, Eyal. Do we have any more questions for Paolo? Let me have a look at the chat. Okay, I can't see any more questions. Well, if there are no more questions, let's thank Paolo again for this wonderful talk and for fielding so many questions.
Thank you very much. Sorry for being a little bit
no.
time.
Yeah, no problem. We have Antonio Lorenzen from, I think he's from Milan speaking next week. He's a PhD student of Alberto Canonical. So I hope to see you.
He's from Pavia, to be precise.
Oh, right. Yeah, because his email address is UniMB, so I thought it was Milano Bicocca. But
Bicocca, then, yeah, you're right. It's another university.
Yeah, not your department.
Yeah.
Yes, so he'll speak next week, and we don't yet have a speaker for the week after that. So if any of you want to speak or know someone who want to speak, just send me an email. Okay, thank you all of you.
Thank you very much, and I hope to meet you in person at some point.
Yeah, soon, as long as planes keep flying.
Let's hope that, I mean, the situation improves.
Yeah.
Thank you very much.
Okay.
Bye. Oh, hi, Awi.
Bye.
Bye.